here is our plan for, Harsh is here. Good. For the next few lectures. So today, after a few clarification on DPLLT, I will give you an overview of Simplex. And depending upon how much time that if I end up finishing earlier on the Simplex overview, Madhukar may possibly give some introduction to ReluPlex, which is actually a special purpose decision procedure that combines Simplex and Relu-like things. I mean, Relu activation function, the logic required to model Relu. Okay. And Wednesday, there is no class. Friday, there is what we planned was that Madhukar will do Simplex and some specific techniques, special purpose techniques that people have come up with for scaling verification to DNN. But we are taking a little bit of a different track because we have, after some deliberations among us, the three of us, decided on a topic for your project, which will involve applying the verification techniques that we have discussed and will be discussing to doing verifying properties of recurrent neural networks. Therefore, even before we discuss ReluPlex and some other topics related to either SMT or even abstraction, refinement, scaling of verification to DNN, we want you to introduce you to what recurrent neural networks are and what verification of doing verification of RNN entails. Okay, so that you can start thinking about your project. So next Monday, that is November 15th, we will publish the contours of the definition of your project with some degree of details. Okay, and November 17th. So the two ReluPlex, which and the scaling technique that I mentioned about using abstraction for verifying DNN discussed. Beyond November 22nd, there's a whole, it will be a mix of these things is what I am planning. There will be some presentations of special topics related to maybe getting into, because we only scratched the surface of SMT. So we may discuss a few more decision procedures that go into SMT, and also doing some follow-up on some of the topics like DPLLT, DPLL, and Simplex or ReluPlex that we have, that we present, okay? And those follow-up presentations, I'm planning that you will be giving, each of you, on after reading, after you go through some supplemental reading, okay, which I will give you the details of soon. And it may also involve presentation by us on some topics of SMT that is not covered. Some of which I've already listed here: ReluPlex and abstraction refinement for DNN. We'll also discussion more on related to project and elaborations of it. Some of those lectures will be in defining details of project more, in more in more depth, and it will also involve some presentation by you on your project status. Okay, so that we so yeah, so we'll make sure that you're making enough progress, or you are stuck in some places and you want some doubts to be clarified, and so on. So it will be those presentations. So are you all there? Hello?
Yes, sir. Yeah.
Okay. I don't know. Something happened with the internet here, and there was a momentary thing. So let me start recording. So everyone is there, I am assuming. So because I can see everyone. Although Harsh's icon is a little bit weird. Harsh, are you there?
Sir, I think I'm joining from phone. That's why it's a different icon.
Okay. Okay, good. Okay, so that is the so here is what I have planned. At least, this. See, we have discussed CDCL and DPLLT, which is extension of CDCL in the presence of solvers. We'll be talking about Simplex, which I understand all of you have seen it in your.
So you're not sharing your screen, I think.
Oh, I see. Okay. Thanks for reminding. Yeah. So what I was saying was, as part of what I mean by follow-up presentation, this is what I have in mind. Okay, there are three of you, and it is mostly involves kind of after we give, so after we just following up on reading and presenting some additional material on a topic that we have already covered. Okay, the three topics I have in mind is exercises. I'm sorry. We have done CDCL, we have looked at DPLLT, and then I'll be covering Simplex today. So for example, I mean, although I give you an overview of Simplex, what I want is for you to maybe read up on why the simplex algorithm that we discussed in class, proving soundness and completeness of simplex, or giving a presentation. So there is already, I'll give you references to a paper for you to read that and present why, specifically why simplex terminates, and when it terminates, why it returns the correct result. Similarly, for CDCL and for DPLLT, I just want you to see DNN verification can be done either using an SMT solver, which really combines DPLLT and simplex, or Madhukar will be covering another special purpose procedure, decision procedure called ReLUplex, which is supposed to be much more efficient. So maybe you will run some experiments on that and then present what is the difference between those two things, those two methods. So which means this will really be a follow-up of on getting a little bit in depth into some of the topics that we have already covered in class. Okay, and don't get tensed up that you have to make a presentation. I mean, as long as you lead a discussion in some organized fashion, will be happy. Okay, so that you will encourage you to read the supplemental material, and then gives you an opportunity to make a presentation and lead a discussion in class. Okay. Now there was a question about quiz. I haven't discussed with the other instructors here as to what we want to do for the quiz. What I had in mind was very simple, some simple exercises that you will do on some of these SMT topics that and verification topics that we have gone through. I know that this detailed presentation on topics was not planned, so we can, I'll discuss with Madhukar and Diganta as to what we have planned, and even if there is a quiz, it will be a small one later towards the end of the course. Any questions on that? Okay. Seems to be something. Okay, thank you. You're welcome. Assignment 2, as I've said, assignment 2, we plan to get it out on Wednesday, and that will involve you to design a DNN for a problem that will be that we will define. Train it to be a small game, implementing a solution to a game, a board game as a DNN, actually be tic-tac-toe, and verify using verify using an implementation of ReLUplex in a system called Marabou, the verifying certain properties about that we will give you about the that your DNN satisfies those properties, and that's what will be assignment 2. Okay, that will get you warmed up for using Marabou, which you will have to use extensively in your project. So this will be a warm-up exercise for that to do the project. Okay. So any questions on this plan? So that's the rough plan. Yeah. So Madhukar and Diganta, I have put your names also there. We had discussed some of it. So if you wanted to add anything.
Yeah, sure. So yeah, nothing. Yeah, I don't have anything to add.
Okay.
Neither from me, sir. Thank you.
Yeah, I just wanted to, before I move on to simplex, wanted to make sure that the certain things that I stated, I might not have stated very clearly, and I want to make sure that you understand that. So I'll ask you, some questions, and make sure that you understand. So the Boolean, okay, does everyone understand the Boolean abstraction of the SMT formula that DPLLT is trying to prove? Okay. So the Boolean abstraction of the formula is denoted by the blue formulas in here. Harsh?
Yes, sir.
Yeah, so you understand what B1, B2, B3, etc. stand for, correct?
Yes.
Okay. Now, so then, so what the implication graph that is generated is one that is generated by, the implication graph is by the t-deduce black box. That does, in addition to BCP, okay, after you make decisions on these new preposition variables that are introduced, so it does, BCP. While it does that BCP, it also does something called theory propagation. So, Ameya, I want to ask you why, these are explicit decisions, the ones noted in green. How is not of B3 derived? Okay, that is derived by theory propagation. Okay, can you tell me how that is derived?
So when you put it in clause 8, you get, so if you put the values of not B5 and not B1 in clause 8, then you get B3, right? That's what your question is?
Yeah,
right?
inside what? You put that inside?
Inside clause C8 in the,
well, if you put, well, no. Okay, I should go one step. Yeah, okay. Okay, so let me, so actually the clause 8 is not there, okay? The original clause is only this, yeah? The original set of clauses is only 1 through 7. So this clause 8 is showing up only as a result of this orange color thing that is derived, okay?
It's a learned clause.
Yeah, it's a learned clause, but how? Not, but how? What is used in learning that clause? See, in CDCL proposition, you learn a clause if through conflicts, okay? If you notice, there's no conflict here, okay? But you still learn a clause, okay? And that is what is different here in t-deduce, okay? From the normal BCP that happens at the proposition level. And this is done through theory propagation, okay? After each decision that you make in here, you check using the solver, which in this case is an LP solver, okay? To see if those decisions, when refined into theory atoms, conjunction of the theory formulas, are consistent, okay, that they are satisfiable. And also it says if as a result, if they are in the case where there's no theory conflict, it asks if it can derive some new literals that exist in the in your current formula. And B3 is a theory literal. By a theory literal, I mean a theory atomic formula that exists in your original formula. So that is generated as a result of theory propagation. Okay. So it is a learned clause, yes, correct, but not due to conflict, okay, due to conflict, but rather due to theory propagation. That is, as it asks the question, the solver, as a result of some of the decisions that I have made on theory literals, can you conclude something which I don't know, earlier? And B3, that the fact that B3 cannot be true is something that is deduced via consultation to the theory solver. Okay, so that is yes.
So this B where not B3 is returned by that particular whatever particular theory we are solving. By
exactly correct. Exactly. Yes. In this case, they are the LP solver. Yeah.
Okay.
I mean, yeah, how you do that, so we assume that, the theory solver is able to do that. One way that you could do, I mean, is, what the literals in your theory literals that are of interest, that belong to a particular theory, appear in your formula. So you could kind of enumerate for each of them, or check that if that follows or its negation follows. But there may be other more efficient way of doing it. Of course, you're not interested in all possible consequences of those decisions. What you're interested in are specifically those that, consequences that of theory literals that appear in your in your formula. So that is another way to do. So you're right. Okay. So yeah. So that is how it is learned. It is a theory. It is done via theory propagation, and it's a learned clause that is derived by consulting your theory solver, not due to a conflict. That's the point I wanted to make. And then that can trigger more literal propagation due to traditional BCP on these propositional the clauses in the propositional abstraction. And that's what is happening here. All these gray ones are propositional implied decisions derived by traditional BCP, not using theory solver. Okay, and that can then result. So all these decisions, for example, even this decision on B2, which is actually a propositional variable, denotes a theory literal. It's a theory literal. Is now derived as a implied thing. So yeah. So now you detect there is a conflict. Now this is once again a theory conflict, because so far A1 and A2 were just propositional variables. Now the moment a decision is implied on a propositional variable denoting a theory literal, then you will have to consult, okay, your theory solver also. So that's why this is a theory conflict, okay, not a traditional Boolean conflict, which can also happen, okay, if it is involving only propositional variables. The moment this BCP is making a decision, in this case an implied decision on B2, there is a conflict. Okay, so that's why this conflict is a theory conflict. Why, Harsh? Why am I? Oh, Devjit, that's your turn. Yeah, why is this a theory conflict? Okay. Yeah, in the interest of time, since you are having problem with your microphone, I'll explain. So any conflict that you get after consulting, as a result of consulting your, sending it to the theory solver to see if the decisions that you have made, either explicit or implied decisions as a result of BCP that results in a conflict is called a theory conflict, because it is determined not as a result of a propositional conflict, but rather it turns out that B5 and not B8 is B2 is derived as a result of BCP, but that you cannot, okay, that is in conflict with B5 and B8 due to theory checking, okay, as a little theory, and this is theory. That's theory conflict, okay.
So like if you have some learned clause by theory in the graph, so then it is then we can say we say there is a theory conflict.
Yeah, say that again. If I missed what you said. Yeah.
If you have some clause which was learned by theory, which was given by, so for example, this knot of B3 we were given by the theory solver.
Yeah, that's a valid consequence of some of the decisions that you make. Yeah.
Yeah, but this so if you do a cut which has
yes. Yeah. So you're exactly right. This theory conflict, it is checked by consulting your theory solver, but the derivation is done by using a cut. Okay.
Okay.
So because there is a conflict here, but the source, the checking of the conflict is not due to some propositional conflicts, okay, but rather due to I think there is no conflict here. When B2 itself was generated, there's no propositional conflict here, okay, and it is conflicting due to this partial assignment. Every time that a new explicit decision or an implied decision is derived, you have to consult. Okay, that is what early pruning involves. So now, and that is also done by sending all your theory literals that you have made a decision on to your theory solver, and then there is a conflict. Okay, once you recognize a conflict, of course, your implication graph will be analyzed using the analyzed conflict, and this will be derived as a conflict clause through the analysis of this implication graph. Okay, and that's what happened. And because B2, as you know, the conflict clause that you generate, this one B2 happens to be, the node B2 happens to be a UIP, and that's why this conflict, which was due to a theory violation, was derived by analyzing the implication graph. Okay? That's why such a thing is called a mixed Boolean theory conflict, because the source of it is not a conflict at the proposition level. It is being derived after checking, consulting the solver, but it is derived, unlike 8, via analysis of your implication graph. Okay. Yeah. So that's what is the difference between 8 and 9. Okay. Both are learned clauses. 9 is obtained due to detection of a conflict at the theory level. 8 is due to theory propagation. Okay. So there's one thing here, okay, in addition to, because as per the UIP analysis, 9 is what will be added, okay? UIP based analysis of the implication graph. Now, if the UIP happens to be an implied theory literal, then, the heuristic says, okay, you get whenever this is the UIP happens to be just due to a propositional thing, then you stop there. But here, why add 10? 10 is also a conflict clause involving UIP, which is actually a decision at the current level. Okay, that's another thing. Now, in this case, the reason that it is added is because so that one, since B2 is a implied literal involving theory clause, I mean, some heuristics in DPLLT say, oh, if the UIP happens to be a theory literal, then also add things which are based on the explicit decision. Okay, so that's what. So it is adding some additional theory, as additional conflict clauses as well. That is a UIP involving the decisions that are made. Okay, there's nothing wrong in doing it, and I think this is just a heuristics in the case of theory conflicts that you get. Yeah. So yes, this is what the thing is. So the new clauses that are added here can be either due to theory propagation, that is one difference, and the other thing is, or it can be due to conflicts, theory conflicts that are checked by your theory solver, but the derivation is done by analysis of your implication graph, much like what analyze conflict was doing. After that, then you backtrack to the earliest level among all the conflict clauses, and therefore you backtrack to this B1. So the only difference in this thing is that you will add more. I mean, the heuristics here says that you add more conflict clauses. Okay, if your UIP happens to be a implied theory literal, that is the only difference. And your backtracking then involves based on backtracking level is based on this based on the conflict clause that contains the decision literal as opposed to the implied literal, both of which are asserting clauses, but because this is the heuristic that's followed, so the decision to backtrack will be to B8, okay, which is the sorry, not even B8, to B8, okay, and all the intermediate decisions made at the other levels are undone, okay, and then your BCP then proceeds. Okay, so that is the difference. Okay, so that's what I wanted. I just wanted to re-emphasize how these. I wanted to make sure that you understood how all these clauses that were learned. All of them are learned clauses. Some of them are due to analysis of your implication graph. Others due to theory propagations. That's the distinction that I want to make sure that you understood. Okay. Yeah. So that's that's all I wanted to make. Any questions? Okay. Yeah. Yes. So that's. Okay. So I will stop here. And I will now move to. Yeah. In the last class, somebody was missing. Was it Hirsch who was missing? So the other two.
Yes, sir. It was me.
No, that's okay. No. I just wanted to be sure that you have also seen Simplex before. The other two said that they had taken some course in which they had seen Simplex. So I wanted to ask the same question to you.
No, sir, I haven't seen Simplex.
Okay, in which case I will go through a little bit more slowly. And Yeah. So simplex is an algorithm that is used to solve conjunction of such constraints, linear inequalities over real variables. Okay, there are extensions to integer variable, when the variables are ranging over integers. But what we are discussing here is simplex procedure for solving conjunction of linear inequalities. Okay, you start, of course, with what we are interested in is actually, yeah. So what we have discussed now is DPLLT, which works for arbitrary Boolean combination. Okay, so but the theory solver that is used is always for the conjunctive fragment. Okay, so you could have these kinds of formulas. That's what we're interested in. But so the DPLLT is uses a theory solver, and with the assumption that the theory solver only needs to solve the conjunctive fragment. Okay, so what the one pre-processing step that is done is you look at all the terms that appear here. Okay, so these non-variable terms in your linear terms, linear arithmetic terms that appear in the formula, they are equated to new variables. Okay, and then you make that, I think. So that's why. So that is one. So we introduce new variables called additional variables or dependent variables. Okay, which will for every term, linear term that appears in your original formula. Okay, and that's what this does. Okay, that is one. So when viewed as and we assume that there are no disequalities. They are all, if there are disequalities like this, they are represented in this fashion. Okay, so this is one pre-processing step that it does. Once you do that, then what you have is one part which equates all the these additional variables that you introduce to the terms that they are supposed to represent. So in this case, x plus y, and these are the two x plus y, x plus 2y, and all these things. Okay, so and that's the first step. Okay, since we are looking at, okay, so now I'm so you will so that is the pre-processing that you actually do. And after that, now the LP solver itself, the theory solver, is assumed to work for conjunctive fragments, and that's what I'm showing, just that the same transformation here for a conjunctive fragment. So if you have your original formula as this one, so you will look at all the terms that appear in here, and so they will be equated to new variables, and the constraints will then be expressed on the new additional variables that are introduced. Therefore, you have two sets of variables: the additional variables and the original problem variables. Okay, so those are two sets, but they are then in simplex, they are then divided into that set of all variables which contain the program variables as well as the original variables and the basic variables. The original variables and the additional variables will be divided into two sets called basic and non-basic. Okay, to begin with, all the the variables that go into basic and non-basics, they can change over the course of your simplex procedure, as we will see. But to begin with, there will be, the non-basic variables will be the original variables here, x, y, and z, and all the basic variables will be the additional variables that you have introduced. So then, what you have is, the original phi will then be split into a bunch of equations equating the terms involving the original variables to the additional variables, and all the constraints will be expressed on your additional variables, okay, or program variables. And this is what these equations will be what we'll be calling as a tableau. Okay, so it has the rows. The rows consist of So the rows, or each row is associated with a basic variable. Okay, which, as I told you, to start with will be the additional variables, the dependent variables, and the columns will be associated with, every column will be associated with the non-basic variable, which to begin with will be your the variables that appear in your original formula, okay, which are the x, y, and z. So what the, so that is what, so how, what does, so sometimes these equality constraints can also be, by moving the, this the basic variable onto the other side, you can express them as, those equations equated to 0. So solving then such, coming up with the LP problem, which simplex procedure solves, is to come up with an valuation for all the variables, both the basic and non-basic variables, such that all these, the inequality constraints are preserved. The equation, all the equations, assuming the equations are preserved, and also the inequality constraints will have to be met. You have to find a solution to all the variables such that they obey the inequality constraints, while the equation is preserved for all the basic variables. Okay, and the way, so that has to be done simultaneously. Okay, for example, if you had, so to begin with, if there are no terms at all, if every constraint in your original formula was expressed as involved only all the terms here, let's suppose they were only variables, okay, then your problem is that means that there are no, so then you don't need to, suppose there were no addition variables that you had to introduce at all. Then can you see that the problem, the LP problem, is easily solved? Ameya?
Yeah, because they don't depend on any other variables.
So there are no, so the constraints that are imposed, so if they're all just independent variables, you can always adjust them independently. It's only when you have, the problem gets interesting and challenging when you have these kinds of terms, which now in our parlance are equated to these non-basic, basic, the additional variables. It's only when you have constraints terms then satisfying one can have an impact. Satisfying the inequality constraints on one of the terms can have an impact on the other. So you'll have to simultaneously satisfy them. Okay, and that and how simplex deals with when you have such simultaneous constraints which are introduced by constraints on these when you have terms, okay, inequality constraints on terms, which are now expressed as these additional variables. Then what it does is it does take them one at a time. Okay, it adjusts. It considers each of these equations, okay, variables in the left-hand side, where you have the constraints of them. It takes them one at a time and solves, tries to make them satisfying. How does it do it? If there are when expressed like this, if all your constraints are already satisfied, then you have a solution. If you don't, then you will have to make these constraints on S1 and S2. You have to adjust the values of these non-basic variables here, X and Y in this case, to adjust in such a way that the constraints on S1 and S2 here, they're usually the non-basic variables are ones which have do not have any constraints on. S1 and S2 are the only ones that have constraints on. So, and the way that you do is to pick a row which violates, and that's what is the pivot and update operation. Okay, so you pick some row which the basic variable whose constraint is not met. Okay, and then you adjust, and you will also pick one of the non-basic variables to adjust the value of the non-basic variables, so that you will you will fix the you adjust the value of a chosen non-basic variable such that the constraint on the basic variable is met. Okay, so for example, here, if you start with the initial assignment of where all of them are assigned 0, then S1 is 0 as well as S2. S2 is 0. Okay, so the constraint on S1 is preserved by this initial assignment, but S2 is not. Okay, and therefore you will have to fix S2 by some adjustment, and that is what the pivot operation does. But after adjusting one of the non-basic variables to meet the constraint on the chosen basic variable, what you do is there's a possibility that the constraint on the non-basic variable may be violated. In order to ensure that that thing is taken care of, you flip. Okay. In addition to adjusting, the pivot operation involves adjusting the value of a chosen non-basic variable, and after you adjust, then you make the non-basic variable. You flip the non-basic variable with the basic variable that was chosen, and you then transform. Yeah, so in this case, S1 was the one that is violated, I guess. Correct?
S2 was violated, sir.
S2 was violated, and therefore you will have to, so you do that by fixing X in this case. Okay, so you have to flip X with S2. Okay, and with S2, which is what you've done, and then you will, readjust this equation so that you will express all the new now basic variable that have introduced, which is x, in terms of the new set of non-basic variables, which had y and z and s2, okay, which got flipped. Okay, so this is just equational transformations. Okay, so that the equations are always they define the new set of basic variables. And what simplex involves is it repeatedly does this operation until all the the basic variable, the constraints on the basic variables are satisfied. Okay, and in which case you declare it is sad. But if you ever get to a situation where you still have some basic variables whose constraint, inequality constraint, is not met, but you're not able to adjust any of the non-basic variables you're not able to fix them such that you can make the constraint left, then you declare that it is not satisfiable. As long as you have some non-basic variable whose value can be adjusted to fix the constraint on a basic variable, you continue. Okay? And an additional thing that it does is, in order to guarantee termination, is that it fixes a certain, and the order in which, since there can be multiple non-basic variables which are whose constraints are violated, and which one you pick to fix first, that is a question you can face. Or you can have there are different ways, different choices available among the non-basic variables to fix your chosen basic variable. For example, in this case, we could have either chosen x or y to adjust in order to fix S1 to meet its constraint. That, when you have multiple choices available to you, then your choice of which variable to satisfy or to adjust will have to be done based on a fixed ordering on the variables. Okay, and that's how you do anything. So that the variable that you choose will be the least variable in this ordering, and you will see that is needed to guarantee termination of the algorithms Okay.
So let me get the algorithm. So like we just, first of all, we basically set all of the values to some number like 0. And then we continuously adjust those variables until some of them is satisfied.
Correct. And that, yeah, the pivot operation is that, involves multiple steps. One is we have to first check if any of the basic variables are, any of the basic variables have their constraints, violated. Okay. Yeah. Then you pick one among them to fix. How you fix them? You will have to pick a non-basic variable. Okay. And the way the thing is that the non-basic variables, during the procedure, the non-basic variables are the constraints on them would have already been met. Okay. If there is a violation, it will be only one among the basic variables. Okay. So the pivot operation, the answer to your question is the pivot operation involves checking first if any of the non-basic variables violates its constraints. Okay. Its inequality constraints. If so, you will have to pick you have to choose one basic variable to pick. Okay. And then how you'll have to choose also a non-basic variable to adjust its value in such a way that you can make the constraint on the basic variable chosen to get it to satisfy. Okay. Once you make those choices, then you do the adjustment, you get new set of values, okay? And then you flip the two things, which will get you a transformation on tau1, okay?
Okay.
Yeah.
Sir, but how are you sure that this will, like, you will either get sat or unsat?
Yeah, that's right. Okay, so first let's try to understand in this class, okay, what the procedure is, because there are lots of details that we'll have to get through. Once we have an example, then I'm sure you will have the question as to why it should be such a, procedure terminate at all, okay? And when it terminates, why, if it, at least the condition of when you will declare it to be sat and unsat will be very clear. There's this question why it should, when it really terminates and gives one of these results, why it should actually be a satisfying assignment. Okay, both of them, those questions will be there. Okay, so we will address that. Okay, so in order, before we address that question, let's understand. I'm sure that I said a lot of words, things in words which are not yet clear. Okay, that I will do through an example, okay? And first using an example, then I'll show you the actual code and what it has. Because even if I show you the code now, there's lots of details for you to digest that you won't understand, okay? But first, so what I want you to understand is, I think viewing this as a constraint solving problem on solving these constraints, viewing them as viewing the solution space on a solution, the possible solutions in a Euclidean space will be very instructive. Therefore, first let me explain that. Now, in this case, it's a problem involving two variables. Okay, before I showed a problem involving three variables. To make it simple, let's have two variables. Then your solution space is in two dimensions. Okay. So so this is the set of constraints that you have. Okay. So it's x. So there's x plus y, 2x minus y, and minus x plus 2y. Those are the three terms, and that's why we have three basic variables, okay, additional variables denoting them, and these are the constraints on S1, S2, S3. So each of these equations here, they represent a line, okay? The value satisfying each of those equations. These constraints here, they, such inequality constraints, they, represent the certain region. They are actually called half spaces, which are planes. Okay. So this one, yes. So each of these constraints, for example, S1 greater than or equal to 2, it represents this entire region on the right side of this line, S1. Okay. The line representing the equation S1. Similarly, the constraint on S3 represents the area above the line S3. And similarly for S2 and S1. So the conjunction, the solution space for this entire LP problem is something that satisfies a conjunction of all these three constraints. So that is this region. Okay, in multi-dimension, it will be something called a convex polytope. Okay, but here that will be like once again here it will be a plane in two dimension. Multi-dimensions, in 3 dimensions it can be a polyhedron. In multi-dimension they can be what are called hyperplanes. Okay, so this entire the shaded region is your solution space. Okay. So what simplex problem, simplex procedure algorithm, when you implement what the pivot operation that I just now explained, you start, okay, so here you start with the origin where setting everything to 0 is the point A, okay? And what it effectively, each time you do the pivot operation, you pick one basic variable represented by an equation whose constraints are not met. So here, when you start with this origin, all three base constraints on all three basic variables, S1, S2, and S3, are violated. Or maybe S2 is, oh no, S2 is preserved because that S2 line passes through A. Okay, certainly S1 and S3 are violated. Okay. Therefore, you will have to pick one of those variables to fix to make it satisfy its constraint. That is done by picking by adjusting the value of one of the basic variables, which here to begin with will be X or Y. So it kind of involves the pivot operation, involves adjusting. In this case, if you pick, say, X to adjust, you can adjust, move, adjust X to 2 to make this S1 get satisfied. Okay, because 2 plus 0 will be will make S1 to be 2. So that involves, like, it is the equivalent of moving your after each operation, the pivot and update operation, you will be moving these points. Okay, so since you pick S1 to make it satisfied, so you will now move it to here. And then you will do this flipping operation, and then you will so S1 will be replaced with X. Okay, S1 becomes the basic variable. So you have the effect of moving these points to these intersection points. Okay, and finally you go from A to B, and after that S3 will still continue to be violative of its constraint, and then you will move to C. Okay, that's the kind of thing that happens. So we'll be enumerating all these extremities of your solution space. This is intuitively I'm describing, okay, through this pivot operation, and you can do. So as you can see, there are various, depending upon the choice of your which basic variable to pick, you pick to fix, and which non-basic variable you pick to adjust to make the basic variable. You can go from A to B to C, that is one, or you can go from A to A to this intersection point here that I'm pointing on the cursor, okay, which I've not named, okay, and then you can move to C, or you can move from A to this negative point here, and then you can move to C, and so on. Okay, so that's basically what is what is happening. You know? And by doing one at a time, you are fixing one thing, and the so that is what is happening. Now, maybe this will give you a little bit of answer to someone who asked the question as to why it should terminate at all. Of course, it may not terminate unless you ensure you can end up going from A to B back to A, from A to B back to A, and so on. That is one way that you will never get to something. Or they might be, you need to be making progress while you are moving from one of these extreme points to something which gets to a solution. So these two things, although you do the pivot operation by picking only one variable at a time, the algorithm indeed guarantees that you will eventually get to that, and that is to a point which will in this region. Yeah. Okay. So after having introduced this, I will do. Then I will go through an example, and I will end this thing. So once again, what does the procedure itself maintains? The algorithm maintains these as part of its state, this set of information. Okay. So given at any point a set of basic variables and a set of non-basic variables whose union is equal to the set of all variables, original variables and addition variables. Okay, it maintains this tableau. Okay, that is the current tableau, because the tableau keeps changing as you do the pivot operation, right? Because you are doing the transformation, because there's movement of variables between the non-basic and basic sets. Okay. And every time you do that, your equation is adjusted as well. So at any particular point, the state involves the current state of the tableau, your basic variable, current set of basic variables, and current set of non-basic variables. Okay. And then there is, at any particular point, you have a temporary assignment, an assignment to each of the basic and non-basic variables. Okay, in your thing, that may not be your eventual solution. That assignment, as per that assignment, some of the some of them might be satisfying their constraints, and some of them may not. Then there is, for each variable, there is as per its constraint, there is a lower bound and the upper bound that it has to satisfy. And there is a fixed strict ordering on variables, which never changes. You pick that variable ordering right at the beginning. Any variable ordering will work, but you will use that fixed variable ordering, okay, during the entire procedure. The initial state of the procedure, initial state will have every original variable, that is the program variables, X and Y, they form the non-basic set. And all the additional variables that are introduced to denote the terms, non-variable terms in your constraints, in your formula, they form the basic set. As I said, beta of xi will be 0. Now this, yes, so that'll be, that's how you will, so the initial assignment will be 0 for every variable. So right at the beginning, that every equation will be satisfied. Okay? So these are the two invariants that are maintained by your simplex procedure. That is, by invariance, I mean after it is satisfied right at by the initial state, and after every pivot operation, these two invariants are preserved. Okay? And that, the fact that these things are preserved will answer will be a partial answer to the question that earlier someone raised as to why this should yield sat, unsat correctly at all. Okay, so the equation is preserved by your beta, your current assignment. Okay, and every variable that is currently in the non-basic set will satisfy its bound. Okay, and about one or more variables in your basics set, which is the row. The columns represent the non-basic set. One or more of them may not be preserved. Okay, so this one, as you can see, if this is preserved after every operation, after every pivot operation, certainly when the procedure terminates, you terminate only if it terminates and gives SAT, you know that you declare SAT only when every variable in the basic set satisfies its constraint. Since the procedure from the, since this every variable in non-basic set is preserved to, is preserved to satisfy its constraints every time. So you will, when you, if it terminates at all, you will, with the SAT, you would have it satisfies. Or the assignment, variable assignment will be such that every variable will be satisfying its upper and lower bound. Okay. Of course, that still leaves the question of why should the procedure terminate at all? And if there is no solution, if it returns unsat, why it should be unsat at all? Okay, so that question will still be there. But these are the two. Your pivot operation always preserves these two things, and that's why, in order to make it preserve, that's why you flip the variable, because after the pivot operation, the basic variable that you've chosen to fix certainly satisfies its constraint, and therefore it is made to go into the non-basic set. As a result of the adjustment to a non-basic variable, you might have violated, therefore you will move it to the basic set. Okay, so before I do this, let me go through this. Okay, and how much time I have. So I'll take another 5 or 10 minutes, and I will end. Okay. So any questions so far? I know that, or you can, if you're completely confused, then you can ask me some questions, or if you're completely confused, wait till I go through this example. But if you have some questions and clarifications or some mistake that I made, please point out. Yeah. Okay, so if not, then I will. So your initial tableau. Yeah, so your initial basic, non-basic variables will be X and Y, correct? So that's one. So that is the columns, okay, X and Y. So, the additional variables are what appear as basic variables, S1, S2, and S3. So you are at A, that's your initial assignment. So this is the variable ordering that I've chosen to use. So with A1, as I said, S2 is already satisfied. S1, S1 and S3 are violated. They're violating their constraint, because S1 has to be greater than or equal to 2, S3 has to be greater than or equal to 1, but both their values are 0, because the initial assignment is this, beta's, denoted beta 0, and that denotes point A. Therefore, I choose S1 because S1 is the lowest a basic variable in the ordering to fix. And I choose X, variable X in the non-basic set, to adjust its value to make S1 satisfy its constraint. So, you will have to, and one more additional thing, and the way that you fix it, you'll fix the values and you will make this, constraint, you will only fix it as small, you will take only as small a step. The adjustment you will choose to make to the basic, non-basic variable will, you will only increase, enhance, or decrease the S1, the variable S1. So the chosen variable, its value, you will do the minimum adjustment required. Okay, so let me put it that way, to fix your chosen thing. Okay, so your the basic variable that you choose, which is violating, could be violating either because its current value is above its upper limit or below its. Okay. By the way, one I mean, I think I skipped that. This procedure that I'm describing right now, it applies. I think I had as a footnote. I forgot to emphasize. This is a the first version that we will be discussing will work only for non-strict inequalities. The assumption is that none of the inequalities is strict. Okay, everything is less than or equal to or greater than or equal to. Okay, and that's when this thing works. So there is an extension that you will have to do for strict equality. So for right now, you assume let's assume that all our inequalities are non-strict. Okay, that is, they are less than or equal to. So yeah, and the adjustment, like I said, you will not fix S1 in an arbitrary way. Okay, you will only adjust it the minimum required so that it will be. So for example, here S1, the value of S1 is 0. In order to make it satisfy, you will have to bring it to 2. Okay, that is the minimum, because it is it has to be, its lower bound is violated. Therefore, you will adjust the chosen. You will adjust X only to bring S1 to the minimal required, which is to its lower bound. And that is determined, and the adjustment theta is what is the adjustment required. And yeah, so you will have to, in this case, you will have to bump S1 to 2, which is possible because X has its coefficient is positive here. If you have to choose, it's positive. I mean, and then so you can increase X to by 2. So once you do that, then you pivot, move X to the basic set and S1 to the non-basic set, and you will, since Y remains the same, X is bumped to 2, you're moved from A to B. Okay? That's what is happening, and you reformulate your tableau. Once, so that you will express, you will move X to be the basic set, and so that now, since S1 has been moved to the non-basic set, you will have to define each of the basic variables purely in terms of the non-basic variables. Okay, so that's what is done. So this is just moving these variables to either side in this equation. Okay, this equation of transformation. That's all that's happening. So as a result of that, now what happens is, as a result of moving from A to B, now S1 is satisfied. So S2 is still okay, because its new value is still greater than or equal to its thing. So S3 is the one that is not satisfied. Okay, so here there's no choice. I mean, you only have S3. Okay, see, one thing you can observe is if one of the original, that is, program variables, which start out to be in the basic non-basic set, gets moved to the basic set, it will continue to remain there, because, I mean, let's assume that there are no constraints on those program variables. Okay, there are constraints on program variables. You can still do it, but for now, let's assume there are no constraints of program variables. So assuming that, it will always remain there, because usually you don't. Even if there are constraints on those independent variables, you can always fix them. So you can always because there's usually no free constraints on them. So that's why they don't they stay in the in the basic set. Anyway, so let's move on. So S3 is one which is being violated. That's the only thing. So, and therefore you choose S3. Here you have a choice. okay, between S1 and Y, which are in the non-basic set, to choose to adjust. Okay. Now, it so happens here in my ordering, Y is, appears before S1. Therefore, I'll choose Y. Okay. To adjust. And once I adjust that, in this case, the thing, I'll have to adjust the bare minimum required to satisfy the S3 constraint, which will take it to the point C. Once I move it to C, everything is, then I will flip it. I will flip it to bring Y into the basic set. And I will readjust all the equations. And you will see S2 continues to be satisfied. And so there are no, every variable in your basic set meets its constraints, okay? And therefore it terminates, the procedure terminates. And based on your invariant preservation, because all the non-basic variables always, they preserve their constraints. Therefore, you stop. Okay. So now I'll take any questions. Okay, these are, I hope I have given you enough details for you to understand. Are there any questions?
Sir, I had a question in your very first example.
This is Harsh?
Ameya. No, this is Ameya.
Okay.
No, so you had given in the very first example, x greater than or equal to 0 is also a constraint in phi prime.
Correct.
So that, so where does that come in?
Yeah. So I think that's, that's a bit of, I know that I said the thing. See, there are two ways of handling it. Okay. See, if there are constraints on your program variables to begin with, okay, there are two ways to handle it. Either you can first adjust those things, okay, or a better way to fit it into this procedure is to, the way that I had said was, okay, for those, remember that I had included, so if there are constraints, I'll tell you one easy way to do, okay, is to introduce an additional variable, okay, to saying S4 is equal to X in that case, okay, and then make S4 as your constraint, okay. That is one way to kind of fit it into this thing. What I had done was I had kind of done an optimization. Okay, this is what you're saying. Okay, this is what you're referring to, correct?
Yes.
Yeah. So here I was doing a little bit of hand waving. Okay, so what I'd said was, oh well, X appears as a constraint. So I will just keep it as is. But the strict way to do it is you will have to introduce. If I were following this thing strictly, I will have S3 equals X, and I will have S3 greater than or equal to 0. Okay.
Okay, sir. Yeah, got it.
That is one way to do. And then what will happen is, as part of your procedure, even the constraints on your independent variables will be taken care of. Okay. Because they will have to be satisfied anyway, because there'll be a row corresponding to some additional variable which is actually equal to that, equal to your program variable, and therefore that on that there will be a constraint. So there will be a row. There will be additional row corresponding to that. Or I think that is the easiest way to fit it into the current thing. Okay, then choosing the origin will work. Okay, as your thing. Okay, so and you will have to fix that constraint on the variable which is equal to your program variable as well. Or as an optimization, you can do the adjustment on your independent variables to start, and then choose that as your initial assignment. Okay.
Yeah. So then we cannot use 0, 0, 0 as the
Then you
start.
cannot
You'll have
use
to
zero.
use something
That's
else.
another way to do. Yeah.
Okay. Okay. Yeah. So depending on what your starting variables are constrained by.
Yeah. So that constraint. So, but then you may not be able to. Yeah. So I mean, they can be, if you kind of over constrain. If you have stupid constraint like, oh, x has to be greater than or equal to 0, x has to be also less than 1, or something like that, then you can end up making that unsat. Okay. Even there can be unsat result even in that procedure. Okay. Because there cannot be any unsat. Then you will declare unsat as well. Yeah. But in any case, yes. So starting with the origin works if you also do these, introduce additional variables corresponding to those program variables on which you have constraints. Yeah, that is one. Okay. Any other question? Harsh, you are the one who should be asking questions because you are the one who's seeing this for the first time. Is Harsh here?
Yes, sir.
So you are a bit confused?
Like
You understand each of the step, what's going on. Yeah, go ahead. Let me.
Yeah, I mean, like, I get the general idea, but I need to look at it again. Like,
Yeah. I think, yeah, that's certainly the case. That is the reason. Okay, all these things I'll say. See, starting with CDCL, I can, CDCL, DPLL, even the simplex, they're not very, they're not that trivial procedures, okay, that you will, look through it once and then you will, I would be lying if I, even now, after so many years of looking at it, I wake up in the middle of the night saying, oh, why is that? Okay, of sad. So don't feel bad, okay, that you don't, because these are not easy procedure. I mean, easy algorithms to understand in one go, and that's why it requires you to review that algorithm on examples and so on. Normally, what I used to do, since we have these, combining these two things, I could give assignment, okay, exercises for you to just simulate these algorithms on examples. But rather than do that, that's why I'm forcing you to read up on these things by making you give those presentation on these follow-up things, okay? That will force you to study these algorithms, okay, a little bit more deeply. And when you do that, you will have to, I mean, as a first thing, go through this example. And I mean, I have a few more variations as an example, just simulate it, okay, and understand it. The same goes for CDCL, same goes for DPLL, okay? So then you will get more questions and the thing. Okay, so, I think I've gone beyond the thing. Yeah, one other thing that I wanted to mention before I leave. So you can see here's the actual procedure. So I will quickly point out one thing. Okay, I won't go through the whole thing because then I'll take a lot of time. So first is select the smallest basic variable. Smallest means in the variable ordering, such that is violating its constraint. That can happen in two ways. It's either less than its lower bound or greater than the upper bound, okay? And since we are assuming these are all no strict inequalities, everything is greater than or equal to, okay? So that's why these are the two cases. So you can either, then you have to choose an xi, a non-basic variable. If there is no such thing, then you return satisfied. Otherwise, you have to choose a variable, a non-basic variable to adjust, okay? And how you adjust will depend on whether you violated the lower bound constraint or the upper bound constraint, okay? And look at this. This is where I'll point out and I'll leave you with, okay? Select the smallest. I already told you that the way that you adjust is you just do minimal adjustment required to bring bring it to either the lower bound or the upper bound, depending upon which one is violated. Okay, but in selecting the non-basic variable to adjust, yeah, you will have to select that non-basic variable, which is strictly less than its, which is within its bound, okay? Strictly within its bound, strictly less than its upper bound and strictly greater than the lower bound. It's a very important thing, okay? Not only you have to choose this smallest variable in the variable ordering, but you also have to choose, you cannot choose that variable in a non-basic variable which you have just most recently fixed. Okay, I mean that which you most recently fixed will be at its limit. Okay, either will be the lower bound or the upper bound. Okay, it is preventing you from choosing that. It is actually asking you to say this condition that it has to be strictly within its bound forces you to not choose the most recently fixed variable. For example, here, if my ordering was different, say, instead of y being here, let's suppose y was after S3 at the very end, then S1 will appear. S1 got fixed now, okay? So it is possible for you to adjust S1 immediately, okay, after this, to do that, okay? Then you can end up going back and forth, okay? You go from A to here, B, A to B, so you can never, that is one possibility for you to violate the terminating condition. Okay, I'll leave it at that. Okay, there was somebody who asked a question, so. Oh, you have a class right now. I'm sorry. Okay, hard end. Sorry. Okay, so I'll stop. Sorry, I forgot about that. I thought you had it only on Wednesday. So I'm sorry about that. So I will end here. Sorry. So I will. I mean, hold on. I mean, make all your questions, and we'll get resolved in the next one. Sorry about that. I missed it. So yeah. I'll stop share. Yeah, make a note of all your questions. Sorry, because I don't want to have the discussion